Hello and welcome back to another episode of Math with Sohn. Today we're going to be talking about springs and dealing with simple harmonic motion and doing some correlations with that and pendulums and so on and so forth. So, one thing that you need to realize is that there is a force that is always going to be acting on the object in the direction towards the equilibrium. Okay, so with a pendulum, that force was gravity, and the string's length and the tension between the string on the pendulum forced it to go back to the equilibrium position. With a spring, it's just the fact that the spring has like this spring constant force that is forcing it to kind of want to go back to equilibrium over and over again. So that spring's constant K is different for each and every spring, and that constant K is dictated by Hooke's law. And it's a negative because it's kind of want to go back towards equilibrium, but in most cases you just deal with it as a positive. And x is referring to that displacement. How far away did you stretch it from the equilibrium position? So like here, it would kind of, if you moved it away this much, then the k would dictate that it will go back and forth, and it will determine how long it will take for it to do its restoring force. All right, some things to pay attention to is sometimes you will call this value from here to here x, and other times you'll call it a for amplitude. They both mean the same thing. It is the distance that the spring is displaced from its equilibrium position. The period is the time it takes to complete one cycle, just like before, and the frequency, just like pendulums, is the amount of cycles it can complete per second, and it is measured in hertz. Okay, so the period of a mass spring system is 2 pi, the mass divided by the spring constant. So sometimes you'll have to utilize Hooke's law, which is, I wonder if there's an E in that. Hooke's law, Hooke's does have an E. Hooke's law, which would be negative fx will equal the force. So sometimes you'll need the negative kx. Negative kx will equal the force. And it also relates very similarly to the pendulum's period. The pendulum's period is the square root of L divided by g, because gravity is the force there. So a lot of similarities. Here we have mass divided by the spring constant, and here we have L for the pendulum. For a pendulum, you have L, the length of the string, divided by gravity. All right? So period and mass are directly proportional. More mass will mean that you have more period, where K is inversely proportional because the spring, if it is stiff, it is going to have a very short period and therefore a smaller period of oscillation. An equation sometimes used for oscillation, you're not given this equation on the AP exam, and I disagree with this guy. I think, and I've seen it in a few places, where that is not included, where it's the amplitude cosine of the angle, its velocity, the angular velocity times time. And you can get your angular velocity by doing 2 pi divided by t. So I have seen the amplitude cosine of 2 pi over t, the period, times t. Now, all of this is kind of unnecessary, but it kind of makes sense because if you think about it in terms of position, the regular cosine graph looks like this. And let's say you pulled it a distance of like, I don't know, 2 meters away. And as the spring, if there's the spring, if you pulled it 2 meters away this way, it is going to want to restore and go back the opposite direction, which is why it gets back to 0 for position, and then it goes to like negative 2 meters. This would be down here at negative 2 meters, and then so on and so forth. And this would represent time, okay? So the spring, in theory, will go back and forth forever. That is what makes it a simple harmonic motion if you neglect to consider any friction. All right? So with that in mind, just like before when we dealt with pendulums, in its furthest stretched out state, it is going to have a kinetic energy of 0 and a velocity of 0. And then it will start moving and wants to go back to equilibrium, start moving back towards the left, and all of that potential energy is stored up in the spring. And then it gets back to equilibrium right around here, assuming this is equilibrium spot. And at that point, it is having its maximum kinetic energy. All of its energy is going to be in the form of kinetic energy. It's as fast as it's going to be, and then the potential energy is 0, and then it continues moving to the left, it gets compressed, and all of that energy gets compressed and stored up again, its maximum potential energy again, and then it gets released, and then back and forth and back and forth forever. Okay? So that's just the basic formulas and the basic idea of what a spring is. Just think of it going back and forth, boing, 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 forever. When it's in its compressed state, it wants to go and push outward. When it's in its stretched state, it wants to pull inward. All right, so compressed, push outward. Stretched out, it wants to pull back in, and it can, in theory, do this forever. And the thing dictating it is the spring constant based off of Hooke's law. All right, next video, we're going to be doing some examples. The examples will deal with how to use these formulas, and I look forward to seeing you then. Bye.